All right, guys. In this section, we're going to be discussing the topic of continuity. And even though this is not a new concept for us, our knowledge of limits are going to allow us to give a more formal definition of continuity. If you recall from your algebra course, you would think of a continuous function as a function whose graph could be drawn with a pencil without lifting the pencil from the paper. So in other words, if you can trace the graph of a function from beginning to end without lifting the pencil from your paper, then we say such function is continuous. If there were no interruptions, no holes, no gaps from beginning to end on a certain interval or on its whole domain, then we say that function was continuous on that whole domain or that whole interval. So before we define this continuity formally, we want to start with three examples here that are going to give us the intuition for the definition of continuity. And these examples are going to show you three cases in which a function is not continuous at a point. So the first one here, if we have a function with a hole there over some interval here, we'll say this is a to b, and we have this hole right at c. Right, we've already talked about the limit as x goes to c of this function. We know that the limit doesn't really care about the function being defined at this point c, but it's still going to exist. We're still going to have a limit here. However, because there's a break there, this is an example of a function that is not continuous, right? So, and we're assuming we're going from the interval a to b here, okay? So in other words, we don't have f of c is not defined, okay? This is this case right here. So when we have a hole, when a single point is not defined in a function, we see that as a hole on the graph, and we say that f of c is not defined. The other example is when we have sort of a gap here, or we call it a jump. Okay, so I'm going to put in circles here, open circles at the endpoints, just to make sure that we're talking about an open interval right now. So on the next example, we'll have a function that has two pieces here, something like this. And then we're going to make the endpoints open right there. Still from an interval from a to b, and this point right here is still our c. So notice how the function is defined there, but there's not a continuity in here. We don't have continuity here, since you see this gap right here, this jump from one place to the other. So then, I mean, if you were trying to graph this without lifting the pencil of your paper, you couldn't, right? You would have to make the jump right here. Now that we understand the concept of limit, we can say here, well, the limit of the function of x as x goes to c does not exist, right? And we know that to be true because this right here is going to a point from the left and it's going to a different point from the right. So we know that the limit is not going to exist, right? So we don't have the problem of f of c not being defined. We do have f of c defined there, but the limit does not exist, okay? So that's the second case. And the third case is very similar to the first one. So very similar to that. And then we're going to have f of c defined somewhere else. So here in this particular case, we do have that the limit exists, as we know, right? The limit exists even if there's a hole there. And f of c is defined, right, at that point right there, but they're not the same thing. So then in other words, the limit of f of x as x goes to c is not the same thing as the function evaluated as c. So when you have this case, we also say we don't have continuity here. So these examples are sort of representative of when you have discontinuities in a function. So then it's going to be the opposite of a continuous function. So based on, we're going to have a formal definition of continuity based on these conditions right here. So if we know what makes a function have discontinuities at a point, then to make sure that a function is continuous, then we're going to have the following definition. All right, so here we have it. the formal definition of continuity. So we have a continuity at one point, and then continuity in the open interval. The continuity on an open interval is going to follow from the continuity of a point, but let's just focus on the definition for one point, the continuity at a point. And again, it's going to have three conditions here, and the three conditions have to satisfy. As soon as one of these fail, then you have a discontinuity, right? Or the function is not going to be continuous at this point, at this particular point, C. So we have a function f is continuous at C when these three conditions are met. One, that f of C, or the function evaluated at that point of interest, has to be defined. So notice how in this first case we didn't have anything defined, so there's, we have a discontinuity. It has to be defined. Number two, the limit of f of x as x goes to c has to exist, okay? Just like in number one, in this first example, it exists there. Number three also exists. It did not exist here on the, so we have a jump, right? That's when you have a limit, the limit does not exist there. So the second condition is the limit has to exist. And then the third condition is basically the number 1 and 2 are equal to each other, right? So then that limit, not only we gotta make sure, we have to make sure that it exists, but we also have to make sure that that limit is actually equal to the function evaluated at that C. Now for the continuity of an interval is just a set of infinite points. So a function is continuous in an open interval if the function is continuous at each point. And we've already seen what that means for each point. So if it's continuous at every point on the interval, on that open interval, then the function is continuous on everywhere on that interval. Same thing applies for everywhere. It's continuous everywhere in the entire real line if it's continuous literally for at every single real point. Okay, so here we have the formal definition of continuity, and again, when one of these conditions fails, then we say the function is not continuous at that point, right? Or also we say we have a discontinuity at x equal to c. Okay, so the two types of discontinuities, we have removable and non-removable. We have a removable discontinuity when, if we take our examples here from the top, when you are able to either define or redefine the function in such a way that you can fill in this hole to make this function continuous. So if you're able to define, in this case, if we just define f of c to be this y value here so that the f of c will fill in this hole, then this function will be continuous then. Also here in the third one, if we're able to redefine, right, f of c is already defined here, but if we redefine f of c such that that point will fill in the hole there, then we'll have continuity from A to B on the open interval from A to B. Now, a discontinuity is non-removable when you're not able to do that. Okay, so for instance, here on the gap here that we have, there's nothing we can let f of c be. Even if we redefine it to fill in that hole, we'll still have that gap. So there's nothing we can do there to be able to put those two pieces together. Okay, another example of non-removable would be an infinite discontinuity. And you can kind of guess what that one looks like when we have vertical asymptotes and you have the function getting closer and closer to those asymptotes, right? As x gets closer to that c, you're actually going to either positive infinity or to negative infinity, depending on the function that you're doing. That's going to be another example of non-removable discontinuity, because there's nothing you can let f of c be so that you can make that function continuous. Now, so far we've been talking about the continuity of a function over some interval, some open interval, right? So notice here the parentheses around the a and the b. So this, you're not actually getting to a or b here, or to f of a, f of b, if those are defined. We're not counting the endpoints here. So how do we understand the continuity on a closed interval? So we've already been talking about the one-sided limits, and so we have said that the existence of a limit depends on the and the two-sided limits here. So the two-sided limits, right, or the limit of the function coming from the left as x is going to some limit point c coming from the left has to match. First of all, they both have to exist, but not only that, but they both have to be the same number. Those limits have to be the same number. Notice here the if and only if in this statement. That means this has to be true if the limit actually exists. And if the limit exists, that means that the two one-sided limits also exist and they actually equal each other, right? Coming from the left, you represent that with a negative superscript, and coming from the right with a positive superscript here. Now, to understand the definition of continuity on a closed interval, we need to understand or be able to calculate one-sided limits, right? Either coming from the right or from the left. Because unlike the open interval, where we just have open endpoints, here we're going to have closed, right, which we represent on the interval with brackets. We gotta be able to check whether the function is continuous at those endpoints as well. So here, if we read the statement, if function f is continuous in the closed interval a to b, close brackets, when f is continuous on the open interval ab, which is the normal continuity that we've been doing, every point within, right, the interval, not counting the a and the b. And on top of that, now we're going to check the two one-sided limits, right? The limit of f of x as x goes to a from the right, because remember, a is the left endpoint. So we got to come from the right. There's nothing to the left of it, right? So then it would only make sense to, and we'll see this on the graph in a second here. Also, we have to have the limit of f of x as x goes to b coming from the left, right? Because b is our right endpoint. B equal to the function evaluated at those endpoints, right? For a, f of a, and for b, f of b. So the function of f is continuous from the right at a and continuous from the left at b. So here we have the graphical representation of continuity on a closed interval. So let's say we have this function here defined from a to b, and this is a closed interval, right? We're counting the a and the b. So we want to make sure that not only everything is continuous here from a to b, not counting the endpoints, and we see graphically it's easy to see the continuity there. So there's no holes, there's no gaps. But we also need to make sure that the endpoints, right? So the limit of this f of x as you go to a from the right is actually equal to this f of a. We want to make sure that that's true. In the same way, the limit, the one-sided limit of f of x, the same function, but now as x goes to b from the left is equal to f of b. Okay, so if that's true, along with everything else in the middle, if it's continuous every point within a and b, that interval, then we have continuity on the closed interval. Pretty straightforward. So this is one way where we get to use the one-sided limits by checking those one-sided limits on the endpoints here of a closed interval. Okay, so now that we know the definition of continuity, we can apply some properties that are just going to follow from the definition, and they're pretty straightforward. We have two functions that are continuous, then and b is some real number, then we have the scalar multiple, right? So if you have a function f that is continuous, if you multiply that function by any constant, that the result would also be continuous. So we have some nice properties, some nice results from continuous functions, and make sure you guys understand this concept of continuity, being able to identify whether a function is continuous at a point or not. And if it's not, what kind of discontinuity we have, because this idea of continuity is going to come up a lot in several theorems that we'll see moving forward. You're always going to get this condition, right? If the function is continuous, if, right, it's continuous. So if you don't have that condition, then the theorem is not going to work, right? For some of the theorems and propositions that we'll do later, continuity is going to be required. It's going to be especially important. Here, again, some nice properties. The product of two continuous functions is also continuous. The quotient also of two continuous functions is also continuous, as long as, of course, the denominator is not zero. there. One example of a theorem that you know of from algebra that requires this condition, that requires a function to be continuous, is the famous intermediate value theorem. If you recall that, this theorem has several applications here, but basically we had a function that said, notice how the condition here is if f is continuous, right? And then we're going to see a lot of theorems that require that a function be continuous in a closed interval, a to b. Again, we already know what that means, continuity in a closed interval, where f of a is not equal to b. So in other words, something like this example here, f of a is not equal to b, right? They're not the same point. And k is any number between f of a and f of b. Then there is at least one number c in that closed interval a to b such that f of c is equal to k. So in other words, this is what's happening here. And let me actually redo a sketch here. Okay, so here we have it. If we have a function f, right, defined on some closed interval a to b, so notice how I'm counting the a and the b here. The theorem says it has to be continuous. Again, you don't see any gaps, anything, so we're going to assume this f is continuous on this interval a to b, closed. And f of a is not the same as f of b, and k is any real number, between f of a, so I'm going to put the k right here, somewhere in between f of a and f of b, right? Then the theorem guarantees that there is at least one number c, there could be more, but there's at least one number c between a and b, the interval a and b, such that f of c is equal to this k. And graphically you can see that here. So again, the important thing here about this theorem is the continuity part, right? So if we don't have continuity, the theorem doesn't guarantee anything, right? And then of course this theorem, in algebra and also here has many applications, one of which is finding zeros or estimating, approximating where the zeros are. Because if you have a function where f of a is negative and f of b is positive, then zero is in between them. And if you know that the function ahead of time that the function is continuous, then you can guarantee that there's at least one zero. So that was one way. And then there's many other applications for the intermediate value theorem. I just wanted to show you one theorem that you've seen before, that you're familiar with, where it uses this word continuous. And again, before we used to have this intuitive idea of continuity, but now we have a formal definition of what continuity at a point and on an open interval is. We also know how to find continuity. Using the one-sided limits, we can find continuity or show continuity on a closed interval. With that, we're going to be able to understand and apply many other theorems and propositions that we'll see later. Okay, here I want to do an example with identifying removable and non-removable discontinuities on a given function. So say we have this function, rational function, x plus 2 over x squared minus 3x minus 10. Now you should be able to graph something like this, but we're going to just try to do this algebraically, and then always keep in mind your algebra here to be able to identify where we have discontinuities here in this function. Okay, so here we have the function factor, top and bottom, and notice how the common factor goes away here, x plus 2. Once we factor the bottom, we see the x plus 2 is a common factor. So we know from our algebra that x minus 2, x equal to negative 2, is going to be a whole right there. And then we end up with this function here. So we can right away see that we're going to have two discontinuities here. One is at negative 2, because the function is not defined there, and also at 5, positive 5, right? Now, if you can already see, this 5 is actually going to give us a vertical asymptote. Our first discontinuity here is x equal to negative 2, and we have a discontinuity here. I mean, again, we know this from algebra that we have a hole there, so we know there's the function is not continuous there. But how do we show that with the definition? We have a discontinuity there since the function is not defined there. So that first, if we go back to our definition of continuity, that first criteria fails here. The function is not defined at f of c, in this case negative 2. So therefore, we have a discontinuity there. We don't even need to check the other two. If one of the three criteria fails, that's enough to show discontinuity. Okay, so for our second point, our second discontinuity is at x equal to 5. And we know it's a discontinuity because the limit of the function as x goes to 5 does not exist. So here we have roughly the sketch of the graph of this function. So we have a vertical asymptote at 5, and then we have a hole at -2. So notice here that looking at a graph, you can clearly see the discontinuities here. You see the hole at -2, and we know that this is a discontinuity because the limit is defined there, but the function is not. Or the limit exists there, but the function is not defined at that point. And for the second discontinuity at 5, we have a vertical asymptote there. The limit doesn't exist. So actually, if we wanted to find the one-sided limits, right, we could say that limit as x goes to 5 from the left of the function here is equal to -infinity, because you see how this is going to -infinity, and the limit as x goes to 5 from the right of the same function is +infinity. Now, it's not just because they don't match, but it's because they're going to infinity. Infinity is not a real number, so then therefore this limit does not exist. So if we wanted to classify these discontinuities, the first one would be removable and the second would be non-removable. So again, why is it removable? Because I can define or redefine this function so that f of -2 is defined at that hole, and that would make this part continuous, right? But the other point at 5, where the vertical asymptote is, there's nothing I can define f of 5 to be to connect those two to make it continuous at that point. So then that's what we call removable. It's actually also called infinite discontinuity, but we're only going to classify them as removable or not removable for our purposes. Now notice here what actually in the definition, what actually makes it removable. It's called removable because literally are removing one point out of the function. When you have that, you can have removal. If you don't, then everything, all the other discontinuities are going to be non-removable, right? You can define or redefine the function in a way that to make it continuous. So we're going to be looking at more examples, identifying discontinuities and using the continuity definition to make sure that we can identify these discontinuities formally and also classify them.